this episode, we focus on the part of security that rarely feels exciting, but almost always determines whether a system stays safe over time: maintenance. Planning secure maintenance for an AI system means you assume the system will change, and you decide in advance how those changes will happen without turning every update into a risky surprise. Beginners often think of maintenance as occasionally installing patches, but in real deployments, it is a disciplined process that includes patch strategy, versioning, and rollback. The reason it matters for CompTIA security AI is that AI systems are made of moving parts: the model, the safety layers, the retrieval sources, the application code, the infrastructure, and even the policies that shape behavior. Any one of those pieces can introduce a new vulnerability, a new privacy exposure, or a new failure mode when it changes. Secure maintenance is how you keep control of the system's behavior and risk, even as vendors release updates and your own team adds features. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A patch strategy is your plan for how you discover updates, decide which ones matter, and apply them in a controlled way. For traditional software, patches often fix known vulnerabilities, but for AI systems, patches can also change behavior in subtle ways. A model update might improve helpfulness but reduce refusal consistency, or it might change how it interprets certain instructions. A retrieval component update might change what content is returned, which can shift outputs even when prompts stay the same. Even a small dependency update can affect logging, authentication libraries, or data handling. A secure patch strategy starts by identifying all components that can change and assigning ownership for watching each one. Ownership matters because updates do not apply themselves responsibly. People apply them, and if nobody is watching, updates become random and reactive instead of planned. An effective patch strategy also separates urgency levels, because not every update deserves the same response. Some updates are security critical, such as fixes for known vulnerabilities that attackers actively exploit. Others are important but less urgent, such as performance improvements or new features. For AI systems, you also have behavioral risk updates, where the update is not a vulnerability fix but can still create security problems by changing model outputs or safety behavior. A disciplined team will have a way to categorize updates and decide timelines, such as immediate action for critical security issues, scheduled action for routine updates, and careful evaluation for changes that affect behavior. The key beginner idea is that urgency is not only about severity, it is also about exposure. A system that is internet-facing and widely used needs faster patching than a system that is isolated and used by a small group. Versioning is how you label and track exactly what is running so you can reproduce behavior, investigate incidents, and control change. In AI deployments, versioning should cover more than just the application code. You want to know which model version was used, which safety configuration was active, which prompt template or system instructions were in place, and which retrieval dataset was connected. If you can't answer those questions, you can't confidently explain why an output happened, and you can't prove whether a problem began after a change. Versioning turns mysterious behavior into explainable behavior because it gives you a timeline of what changed and when. Beginners sometimes think version numbers are just for developers, but in security, they are evidence. They help you show that you applied a fix, they help you correlate incidents with updates, and they help you avoid guessing when you need facts. A particularly important versioning concept for models is pinning, which means choosing to stick to a specific model version instead of always using latest. If a vendor updates a hosted model behind the scenes, the same prompt might produce different results tomorrow than it produced today. That can break safety expectations and create compliance issues, especially if you have validation steps based on specific behavior. Pinning gives you stability, so you can test updates before adopting them. However, pinning also creates a maintenance responsibility because you must eventually move forward to receive fixes and improvements. The secure approach is to pin where possible and to create a regular cadence for evaluating newer versions. That way you get both predictability and progress, instead of either chaos or stagnation. Rollback discipline is the ability to undo a change quickly and safely when something goes wrong. Beginners sometimes assume you can always just roll back, but in practice, rollback is only easy if you designed for it. If you update a model version and outputs suddenly become unsafe or unreliable, you want a tested way to switch back. If you change a retrieval source and it starts surfacing sensitive documents, you want a quick way to revert to the prior index. If you deploy a new policy filter and it starts blocking legitimate work, you want to restore service without disabling all protections. Rollback discipline includes having clear triggers for rollback, such as spikes in policy violations, user reports of harmful content, or unexpected system errors. It also includes rehearsing rollback, because the first time you test your rollback plan should not be during a real incident. To make rollback realistic, you also need to think about what changes are reversible and what changes are not. Some changes, like switching a model version, might be reversible quickly if you have configuration controls. Other changes, like a data leak into logs, are not reversible just by flipping a switch, because once data is exposed, you can't unexpose it. That is why secure maintenance includes change review before deployment, especially for changes that affect data handling. For example, if an update increases logging verbosity, you might accidentally start storing raw prompts that contain sensitive information. Even if you roll back later, the log data may remain in storage. A disciplined maintenance plan asks, before applying a change, what is the worst irreversible consequence if this goes badly? That question forces you to design safer defaults, like minimizing data retention and restricting access to logs. Secure maintenance also needs a testing approach that focuses on safety, not just functionality. When you update a model or a safety layer, you should rerun abuse-oriented tests, like prompts that attempt to override rules, extract secrets, or produce disallowed content. You should also rerun reliability tests, like repeated prompts that should behave consistently. If your system uses retrieval, you should test whether it still respects access boundaries and whether it still avoids pulling restricted content. If your system uses formatting rules, you should test whether outputs still follow them, because broken formats can create downstream security issues, such as output injection into user interfaces. The beginner lesson is that AI updates require behavioral regression testing, not only unit testing. You are testing the system's safety posture as a behavior, not only its correctness as code. Another part of patch strategy is how you receive information about issues. Vendors may publish advisories, release notes, or security updates, and your plan should include monitoring those channels. For internal components, your plan may include scanning dependencies for known vulnerabilities and tracking versions in a software inventory. In AI systems, you should also monitor for changes in terms of service, data policies, or retention settings, because those can affect compliance even if the software stays the same. Secure maintenance treats policy changes as part of the change landscape. If a vendor changes how they store prompts, that could change your risk profile overnight. A mature team notices and responds, while an immature team finds out after an audit or after a customer asks uncomfortable questions. Maintenance discipline also includes documentation that is good enough for humans who were not in the room when the system was built. That means recording what version is deployed, what the intended behavior is, what the safety controls are, and what the rollback steps are. Documentation is not about producing paperwork. It is about reducing uncertainty during an incident. When something goes wrong, you do not want to debate what normal is, because time matters. If you have clear baselines, you can detect deviations faster and make confident decisions. Documentation also helps onboarding, because new team members can understand why certain constraints exist instead of accidentally removing them. In security, many incidents begin with someone making a well-intended change without realizing what the control was protecting against. As you plan maintenance, it's also important to balance speed and safety, because moving too slowly has risks as well. If you never update, you accumulate known vulnerabilities and fall behind on fixes. If you update too quickly without testing, you risk breaking controls or changing behavior unexpectedly. The secure middle ground is a steady cadence with the ability to accelerate when needed. That cadence might include regular review windows, staged rollouts, and an emergency patch process for critical issues. The key is that you decide the process before the crisis, because crises create pressure, and pressure leads to shortcuts. A maintenance plan is a promise to your future self that you will not rely on improvisation when the stakes are high. When you zoom out, secure maintenance is really about preserving trust in the system. Users will only rely on an AI feature if it behaves predictably, respects boundaries, and doesn't surprise them with unsafe output. Leaders will only approve expansion if incidents are rare and well-handled. Secure maintenance supports that trust by making change controlled and reversible whenever possible. Patch strategy ensures you keep up with fixes and improvements without random drift. Versioning ensures you can explain what happened and why. Rollback discipline ensures you can recover quickly when things go wrong. If you learn to think about maintenance as part of security design, not as afterthought cleanup, you will naturally build systems that stay secure not just on launch day, but every day after.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.